This is Dr. D. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today the topic is centroid for composite sections. The centroid can be determined by using three methods: geometrical consideration, method of moments, and graphical method. Geometrical consideration, it is only applicable to the regular objects such as square, rectangle, circle, semicircle, and triangle. And center of gravity by the method of moments. Generally, it is used in engineering application for determining center of gravity or centroid of all the objects. And the graphical method, it is also a third method. It is used to determine the center of gravity or centroid of the objects. But it is a laborious work, generally not preferable when comparing with the method of moments. Hence, today we are considering method of moments for determining center of gravity of bodies as well as the centroid of planes. Now considering an object kept in the XY coordinate plane as shown in figure. Now it is divided into some number of segments having mass m1, m2, m3, and the center of gravity of each element is located at a distance of x1, y1, x2, y2, x3, y3 according to the reference lines x-axis and y-axis as shown in figure. Then centroid of the whole figure is obtained by using the law of mitral moments. It states that the moment created by the resultant force at any point should be equal to the algebraic sum of the moments created by its components at that point. Let us assume here now each element is having m1, m2, m3 are the masses. Hence corresponding weight is W1, W2, W3, where W1 is equal to m1 into g now. Hence the moment created by the total weight at any point should be equal to the moments created by the segments having masses m1, m2, m3 or weights w1, w2, w3. Since g is a constant now, we are assuming the gravitational field is uniform. Hence, according to the principle of moments, we can write it to m into xc equal to m1 x1 plus m2 x2 plus m3 x3. Where xc is the position of the centroid of the whole object with respect to the y-axis, and x1, x2, x3 are the centroid of segments having masses m1, m2, m3 respectively. From this relationship, we can write it now. Xc is equal to sigma mx divided by capital M, where capital M is equal to sum of the masses of all the segments, which is equal to m1 plus m2 plus m3 and so on. Similarly, yc is equal to, that is the position of the centroid with respect to the x-axis. It is given by yc is equal to sigma my divided by sigma m. Using the same principle, we can determine the centroid of two-dimensional objects as here m1 is representing the mass. It is equal to volume multiplied by the density. Assume just it is having uniform thickness as well as the made up of same materials. Hence, the modified equation is xc is equal to m1 x1 can be written as rho t a1 x1, where a1 stands for the area of the segment 1. Similarly, m2 x2 is equal to rho t a2 x2 plus m3 x3 is equal to rho t a3 x3 and so on. So, total mass is equal to rho t into a, where area is representing the total area of the object. So since rho t is the common in both the denominator and numerator, hence the simplified equation is sigma of ax divided by a now. Similarly, yc is equal to sigma ay divided by a and so on. Now, the centroid of composite sections. Here we are determining centroid of composite sections, that is symmetrical section as well as the unsymmetrical sections, by using method of moments. Here I am taking the example is find the CG of 100 mm by 150 mm and 30 mm T section shown in figure now. Now if we observe the object is symmetrically above the vertical line, hence the centroid of T section always lies on this line only now. That is here the vertical lines. Hence the reference line, that is the vertical reference line, is taken as y-axis, and the line which is passing through the bottom of the figure in horizontal direction is treated as the x-axis and represented here lines. Now with respect to this x-axis and y-axis, we have to locate the position of centroid for the T section. Since here now, if the object is unsymmetrical, generally the reference line is one is the bottom of the figure in horizontal, that is the tilted x-axis, and one more line is which is passing through the extreme left of the object and perpendicular to the x-axis. But here it is symmetrical about the vertical lines. Hence we have taken the vertical line as reference lines on which the center of gravity is lying now. So the coordinate of xc is equal to 0, since the center of gravity lies on y-axis according to that symmetrical figure now. Hence here we are determining only the position of yc only. That means where that center of gravity lies with respect to the x-axis as shown in the figure now. Somewhere it is away, just we have to determine it now. So according to the law of moments for the area, yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2. So here now, this object is, this composite figure is, first of all divided into some number of regular figures. Here regular figures stand according to the engineering mechanics. It may be in the form of square, rectangle, triangle, circle and semicircle. And so this figure, the T sections, it can be re-modified into two rectangles, which is represented here, two colors as shown in figure. Here 1 and 2 now. That is here now we are taking this one figure and it is nothing but a second triangle now. Here these are represented as now ABCH is the one triangle, one rectangle. It is represented as 1 now. The second rectangle is represented here GEDEEF now. Now by using the principles, yc is equal to a1 plus a1 y1 plus a2 y2 divided by a1 plus a2. According to that one, a1 stands for the area of the first triangle. The area of the first triangle is equal to, here length is given 100 mm and breadth is given 30 mm. Hence we can take it as a1 is equal to the product of length and breadth 100 into 30, which is equal to 3000 mm square now. Similarly, the center of gravity of the first rectangle with respect to the y-axis we have to take it now. With respect to the x-axis, here the center of gravity of the regular figure always lies here now. For the rectangle, it is the intersection of diagonal or just midpoint of the height we can take it now. That is nothing but here, according to the figure, it is somewhere here now. That is half of the 30 mm now. But we have to locate that y1 position with respect to the x-axis. That means this distance is required now. So this is the treated as y1. That is y1 is equal to, we can take it, since the width of the web is given now 30 mm, the remaining portion it is equal to 120 mm is given now. So the y1 position is 120, y1 is equal to 120 plus 30, it is half, it is equal to 120 plus 15, it is now equal to 135 mm now. That is y1 for this figure is equal to 135 mm, or you can take it to 150 minus half 30 by 2, which is equal to 135 mm. Similarly, for the rectangle EFGD, the length is given, height is given 120 mm and width is given 30 mm. Hence, the area A2 is equal to 120 by 30 mm, which is equal to 3600 mm square. And Y2 is representing the position of the centroid with respect to the x-axis as shown in figure now. Since 120 there now, it is in the form of rectangle. It lies at a distance of 60 mm from the bottom of the figure. That is the half of the height now, which is equal to 120 divided by 2, it is equal to 60 mm. Now the distance of center of gravity or centroid for the above figure, from the bottom of the figure, that is from EF, is given by YC is equal to A1 Y1 plus A2 Y2 divided by A1 plus A2. A1 is equal to 3000 into 125 Y1 plus A2 is equal to 3600 into Y2 is equal to 60 divided by 3000 plus 3600. On simplifications, we got YC is equal to 94.1 mm. That means the center of gravity of the T sections is lies at a distance of 94.1 mm from the bottom of the figure. Approximately, this is nothing but representing the position of the centroid. Similarly, we can take the centroid of unequal angle section is shown in figure. It is not symmetrical about the x-axis and y-axis. Hence, in this case, the bottom of the figure is taken as that is x-axis. That is the horizontal line which is passing through the bottom of the figure is treated as x-axis, and the extreme left it is there like this. This is treated as the y-axis now. Now, with respect to the x-axis and y-axis, these are called reference axis now. We have to locate the position of the centroid now. Okay, you can divide this composite figure in such a way that the obtained segments are in the form of square, rectangle, triangle, circle or semicircle. Here we can make it two rectangles now. You can take like this, one is a rectangle now, that is 1 and 2. Otherwise, you can divide like this, we can get one more rectangle now. Here we have taken that the vertical line is nothing, here this is nothing, one rectangle, and second one is representing the second rectangle now. Using the formula x is equal to a1 x1 plus a2 x2 divided by a1 plus a2, and one more equation yc is equal to a1 y1 plus a2 y2 divided by a1 plus a2, we have to locate the position of centroid. Here xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2. Here a1 stands for the area of the first rectangle and a2 stands for the area of the second rectangle, and x1 x2 represent the position of the centroid of that rectangles with respect to the y-axis. Hence, a1 is equal to 100 into 20, it is given now, which is equal to 2000 mm square now. Similarly, x1 is equal to, that is, this is the position now, it lies somewhere in the middle of this line now. That is how much length is given, width is given, here 20 mm is given now. That 20 by 2 now. That means here x1 is equal to 20 by 2, which is equal to, here we are taking 10 mm now. Similarly, y1 is equal to, the width is given totally 100 mm is given. With respect to the bottom of the figure, it is in the middle, that is 100 by 2, which is equal to 50 mm now. Similarly, A2 is equal to, that is area of the rectangle, that after subtracting 20 mm, the remaining length is only 60 and the width is equal to 20 mm. Hence, A2 is equal to 20 into, here we have taken 60, which is here is given, which is equal to 1200 mm square now. Similarly, x2 is equal to, here we have to take x2 nothing but the position of the centroid of the second rectangle is given with respect to the y-axis. Here already this thickness is given 20, so we have to take 20 because this distance is required now. It lies just in the middle of this rectangle now. Hence 20 plus the remaining is given 80, that is 60. 60 by 2 we have to take it now. That is 20 plus 60 by 2, it is equal to 50 mm now. That is x2 is equal to, we got it 50 mm now. Similarly, y2 is equal to, it is in the middle of 20 mm. So hence is equal to 20 by 2 is equal to 10 mm now. So first you determine the area of the first rectangle, x1, y1 position. Similarly, for the second rectangle also, area as well as the x2, y2 positions we have to determine with respect to the x-axis and y-axis as the reference axis as shown in figure now. Now, according to the fundamental equations, xc is equal to a1 x1 plus a2 x2 divided by a1 plus a2. According to the figure now, it is given by 2000 into, it is given now, into 10 now, plus 1200 into 50 divided by 2000 plus 1200. On simplifications we got, it is equal to 25 mm now. Similarly, the distance between the center of gravity of the section and bottom face is given, a1 y1 plus a2 y2 divided by a1 plus a2, which is equal to 2000 into 60 plus 1200 into 10 divided by 2000 plus 1200, which is equal to 35 mm now. That is, the center of gravity here lies 25 mm from the y-axis and 35 mm from the x-axis. That is nothing but this figure is somewhere it is there. It is not at all lie within the object now. That means the center of gravity or the centroids may lies within the objects or outside the object. It only purely depends upon the geometry of the object. Okay, now center of gravity of a uniform lamina, that is nothing but thickness is equal to here uniform, or it can be treated as a negligible now. As shown in figure, lamina is nothing but here negligible thickness is having, consists of a rectangle, that is here the one is a rectangle, one more is a semicircle and a triangle. Determine the center of gravity of the lamina. All the dimensions are in mm is given. Here, if we observe this figure, it is not at all symmetrical about the vertical line or the horizontal lines. Hence, the reference line should be, one should be passing through the bottom of the figure. The second one is, it should be vertical and passing through the extreme left of the given object now. That means, here now we are taken, this is known as our x-axis now, and this line is representing here the y-axis and so on. Like this. With respect to the x-axis and y-axis, look at the position of the centroid now. Here, divide this object into some number of regular segments now. Regular means already I told it may be in the form of rectangle or square or triangle or semicircle and circle and so on. Here, while examining this figure, we can get 3 segments. So, one is the semicircle here represented now. The second one is in the form of rectangle, and third one is the triangle as shown in figure now. That means that entire area can be divided into 3 segments, consists of semicircle, rectangle and triangle now. Now we have to determine the position of the centroid with respect to the reference lines x-axis as well as the y-axis as shown in figure now. Now if you take the first one semicircle, it is now symmetrical about this horizontal line now. That means the center of gravity lies in the middle of the diameter. Diameter is equal to how much it is given? Here 50 mm is given now. That is, here it is treated as for this figure. The y1 is equal to 50 by 2, it is equal to 25 mm now. That is for semicircular is given. That is y2 is equal to here given 50 by 2 and 25 mm. This is given now. Similarly, x2 is equal to, that is the position of the centroid with respect to the y-axis is equal. Here it is given generally 4r by pi from the diameter. That is, this is the position now. This is the position. That is the standard is given 4r by 3 pi. This is the position of the centroid with respect to the base, that is the diameter now. So here when we are taking this above now, but we are measuring the distance with respect to the y-axis, we can say it is now 25 minus half 4r by 3 pi now. So from this one it is there, I required the distance of this one now, that is 25 minus 4r by 3 pi. So 25, 4r by 3 pi is equal to 25 minus 4 into 25 by 3, which is equal to 14.4 mm. That is the centroid of first segment, that is a semicircle, lies at a distance of, that is the x2 is equal to, according to the notations now, we taken this second figure, it is equal to 14.4 mm and y2 is equal to 25 mm as shown in figure now. The area of the semicircle is equal to, it is equal to pi r square by 2, which is equal to pi into 25 square by 2, which is equal to 982 mm square now. Now for the rectangle now, total is given, just length is equal to 100 mm is given and width is equal to 50 mm is given. The area of the rectangle is equal to 100 by 50, which is equal to 5000 mm square now. And x1 is equal to, it is nothing but in the middle of x2 now, that is x coordinate, it is somewhere it is there now. That is the distance is equal to how much it is now? Now it becomes 50, but we are measuring with respect to the y-axis 25. That is 25 plus 100 by 2. If you take 25 plus 100 by 2, which is equal to 75 mm. Similarly, the y coordinate is in the middle of the height now. Height is given how much it is here now? 50 mm. Middle is nothing but 25 mm. Hence we can take y1 is equal to 50 by 2, which is equal to 25 mm. That is, we got the area, the centroid of their coordinates x1, y1 as well as the x2, y2 be determined. The third figure is there. It is the triangle. Area of the triangle is equal to half into base into height. Base is given 50 mm and height is given 50 mm by 2, which is equal to 1250 mm square now. x3 is equal to, it is given now, here x3 is given now, that is the position here somewhere it is there. This distance we have to measure now. It is equal to 25 plus 50 plus 25, it is equal to 100 mm now. That is x3 is equal to 100 mm. Or 125 minus 25 mm, it is equal to 100 mm. Similarly, y3 is equal to, we can take it as 50 mm. From this base, you have to take it is equal to 50 mm. From the height, it should be h by 3 only now. That is 50 by into 3 now. So, from this relation, we got to 50 plus 50 by 3, it is equal to 67.7 mm. Now, the distance between the center of gravity of the section and the left edge of the circular portions is given. That is with respect to the y-axis. It is given by xc is equal to a1x1 plus a2x2 plus a3x3 divided by a1 plus a2 plus a3 now, which is equal to 500 into 75. That is a1 is equal to 500, x1 is equal to 75 plus a2 is equal to 982 into 75 plus a3 is equal to 150 into 100 divided by a1 plus a2 plus a3, that is 500 plus 982 plus 1250, which is equal to 71.1 mm. That is with respect to the y-axis, the center of gravity lies at a distance of 71 mm. Similarly, the yc is equal to, that is yc is the position of the centroid with respect to the x-axis, is given by a1 y1 plus a2 y2 plus a3 y3 divided by a1 plus a2 plus a3. According to the figure, a1 is equal to 5000 into 25 plus a2 is equal to 982 into 25, 1250 into 60 divided by 5000 plus 982 plus 1250. According to this figure, which is equal to 32.5 now. That means it is at a distance of 32.5 mm from the base, and 70 x is equal to, we got, no sorry, it is equal to 71.1. That is from this one, 71.2, 70 here it is somewhere now. The position of the centroid lies at this position. That is 75. This is the position of the centroid now. That is, centroid is nothing but it is a point at which the total area of the composite figure assumed to be concentrated. Similarly, here we have taken composite means nothing but a combination of regular segments, like it may be the combination of rectangle, square, triangle or semicircle, like that we have taken earlier now. But sometimes some part is also, if it is removed, that is also treated as a combination of two segments. It also comes under composite figures now. So I am taking just some problem here now. A square hole is punched out of a circular lamina. The diagonal of the square being the radius of the circle, as shown in figure now. Find the center of gravity of the remainder if r is the radius of the circle. Now, the diameter is given, the diameter according to problems, the diameter of the circle is equal to, is given, d is equal to 2r, where r stands for the radius of the circle. And one more rectangle is punched in it in such a way that the length of the diagonal should be equal to the radius of the circle now. Now, here it consists of two figures. One is a circle, one more is the square, as shown in figure now. The area of the main circle is equal to, assume A1. A1 is equal to, here pi r square, and x1 is equal to, here r we are taking. Here, as the section is symmetrical about the x-axis, therefore, it is treated as the center of gravity lies on this line, as shown in figure now. That is, it is a one line now. The second one is, this is known as y-axis now. So, x-axis lies, since it is a symmetrical about the y-axis, means the y-coordinate of the centroid is treated as 0 now. That means yc is nothing but not required to determine. Now we have to determine the xc now. That is, xc is equal to a1 x1. But here area is removed now. It is modified as minus of a2 x2 divided by a1 minus a2 now. Since in area is negative now, just you have to subtract, you have to replace the plus sign with the minus sign as shown in figure. Now, the area of the first triangle is equal to pi r square, where r is stand for the radius of the circle, and x1 is equal to, for the first figure, it lies at the center of the circle, which is at a distance of r. Hence, x1 is equal to r, area is equal to pi r square now. It cutout to square is given, the second one, area is equal to, is given r into r by 2, which is equal to 0.5 r square, and x2 is equal to, here, r into 0.5 r, it is equal to 1.5 r now, because it is given, center somewhere is given now, the radius. Here, that means the area of the cutout square is equal to r into r by 2, 0.5 r square, and x2 is equal to, that is r plus, just in the middle of r it is there now, that is 1.5 r now. So xc is equal to a1 x1 minus of a2 x2 divided by a1 plus a2, a1 minus a2, hence x is equal to pi r square into r minus half, a2 is equal to 0.5 r square into 1.5 r, it is equal to pi r square minus half 0.5 r square. On simplifications we got it is equal to r into pi minus 1.5 divided by pi minus of 0.5 and so on. This is our position of center of the given object. Now one more problem I am taking now. A semi-circular area is removed from the trapezium as shown in figure. All the dimensions are given in millimeters. Determine the center of the remaining area now. That is, this remaining area nothing but this is treated as the remaining area, which is represented by using actual lines now. Since this figure is not at all symmetrical about the x-axis and the y-axis, hence this you have to take it, the bottom of the figure is represented as now x-axis and left hand side it is known as y-axis as shown in figure. Now divide this figure into some regular objects like rectangle, triangle, as well as semicircle as shown in figure now. That is like this now. Here if you take one line like this, it is run as a first figure, it is a rectangle, this is the second figure, triangle, third figure, it is a removed part, it is in the form of semicircle now. Now area of the rectangle is equal to 30 into 40 plus 40 now, that is 80 now. 80 into 30, which is equal to 2400 mm square now. Similarly, the position of the centroid with respect to the x-axis and y-axis is given by, first we are taking with respect to the y-axis, it is nothing but in the middle of the length of the rectangle, that is equal to 80 by 2, 40 mm now. Similarly, y1 is equal to this half of the height now, that is equal to 30 by 2, which is equal to 15 mm as represented here now. That is y1 is equal to 15 mm and x1 is equal to 40 mm. Similarly, area of the triangle is equal to half into base into height now. That is the base is equal to here now, it is equal to 30. It is equal to 80. It is equal to again 30 mm now. That is the half into base into height, 80 into 30 by 2, which is equal to 1200 mm square now. Now x2 is equal to here from this one, we are measuring the distance with respect to the here it is there. From the base it should be h by 3, The remaining is nothing but it is equal to 2h by 3 now. Hence, x2 is equal to 80 into here 2 by 3 into height, which is equal to 53.3 mm now. Similarly, y2 is equal to here from this position, y2 is equal to 30 plus again h by 3, that the height is given here now 30 mm, that is 30 divided by 3, which is equal to 40 mm is given now, that is y2. Always you have to take the position of the centroid is lies at a distance of h by 3 from its base position. If it is a base is there, h by 3, that is nothing but 30 by 3 now. From the bottom position, 30 plus 30 by 3, which is equal to 40 mm. Similarly, the cutout circle, the area of the cutout circle is equal to semicircle is given pi r square by 2, which is equal to pi into r is equal to 20. It is given, the diameter is given 40, r is equal to 20 by 2, which is equal to 628.3 mm square now. Similarly, x3 is equal to, here it lies on this line somewhere now. The distance is equal to 4r by 3 pi from the base. It is given. This is the position of the centroid. Hence, it is equal to, this x3 is equal to 40 plus 20 by 2 now. That is, it is equal to 60 mm now. y1 is equal to 4r by 3 pi. 4r by 3 pi, 4. r is equal to 20 divided by 3 pi. It is equal to 8.5 mm. Then, the distance between the center of gravity of the trapezium with respect to the x-axis and y-axis is given by y-axis and x-axis is given by a1 x1 plus a2 x2 minus, because the circle is removed, minus a3 x3 divided by a1 plus a2 minus a3 now. So a1 is equal to 2400, x1 is equal to 40 plus a2 is equal to 1200 into x2 is equal to 53.3 minus of 628.3 into 60 divided by 2400 a1 plus a2 1200 minus a3 628.3, and simplification we got to 41.3 now. That is, if it is there now, this distance is given now, xc is equal to 41.3 is a 40. This on this lines it lies somewhere. This is equal to 41.3 now. Similarly, yc is equal to a1 y1 plus a2 y2 minus a3 y3 divided by a1 plus a2 minus of 3, which is equal to a1 is equal to 2400 into y1 is equal to 15 plus a2 is equal to 1200, y2 is equal to 40 minus of 628.3 into 8.5 divided by a1 plus a2 minus a3, which is equal to 26.5 mm now. That is from the location. Here it is there 26.3. This is the position of the CG of the given composite figure. Okay. This is a summary of the determination of center of gravity of the composite figures. Okay, sir.
Like, share and subscribe. Hit the bell icon for more updates.